Okay, hello everybody. We are going to do one more slope fields video, more with slope fields. And if you would like to play along with the paper, you can find it in the modules and it's literally called More with Slope Fields, but you should be okay if you just want to watch as well. So if you'd like to get it, go ahead and hit pause, go to modules, print it out, and I'll see you in a moment. Okay. Now that we know how to draw slope fields and we've had a day or two to let this kind of percolate in our brain here, we are going to step it up a notch. And the assignment that I have is a Desmos matching activity. So I just kind of want to chit chat with you a little bit about slope fields and give you some more information. Okay, so I have this packet and a slope field is already drawn, and you will not be taking multiple choice college board test anymore in May, but I still want you to understand about slope fields because it's very likely that you'll have to draw one or be asked a question about one. Okay, plus they're cool. So here is a pre-drawn slope field, and the question says, which of these derivatives would have spit out this slope field? So I went ahead and I wrote the derivatives down because I'm not that tech savvy and I'm going to be toggling back and forth between screens here. So I'm going to go to my slope field generator in Desmos. Your brain is going to be your slope field generator, but this will just help me explain this. So the very first one that was given was 1 plus x. Here is what a slope field for 1 plus x would look like. If the derivative is 1 plus x, reminder that the antiderivative is a parabola. So it makes sense to me, specifically the parabola x plus x squared over 2. You can do the antiderivative of this. So it makes sense to me that the slope field looks parabolic. At different places in the field, this is what the slope would be. And you can almost imagine an infinite number of parabolas being drawn in here. In fact, there are an infinite amount of parabolas. The C determines which specific parabola you're talking about. So this is not it. This is not the match. This is what the slope field for 1 plus x looks like. Let's look at another one. Here's what x squared looks like. The antiderivative of x squared is 1/3 x cubed plus c. So the dy dx of x squared would generate the slope field that you see on my screen, and that makes sense to me because the antiderivative of an x squared is 1/3 x cubed plus c, which is cubic. This slope field looks like cubic solutions could fit in here, an infinite number of cubic solutions. It's hard because I can't draw on this, but if I could and I was drawing, you would see a cubic in front of your face. There's an infinite amount of them. It depends on what the C is for which one you're specifically talking about. So this one's not the match. This one is going to be the answer. So I'm going to skip it for a second for the sake of teaching. And we're going to go to choice D, which is x over y. Okay, so here is the slope field generated by the dy dx of x over y. This looks hyperbolic. This looks like a hyperbola. I bet if you separated the variables, if you had a moment and you separated the variables and you integrated this, you would get something with x squared minus y squared or y squared minus x squared. This would look like a hyperbola in solution form because I see something hyperbolic from algebra 2 and from conics from pre-calc on my screen. This is not the match. Let's look at dy dx equals ln y. Okay, so if the derivative is ln y, I don't have this antiderivative memorized, so I'm glad I have a slope field to help me. I could probably rewrite it with exponentials and figure it out, but let's just look at our slope field. If y is 1, If I plug a 1 in for y, ln1 is 0. So every single time that y is 1, the derivative is 0. Notice that in my slope field, every single time that y is 1, I have a horizontal tangent. Let's plug in y is 2. If y is 2, ln2 is some positive number. Notice that every single time that y is 2, you have a consistent, identical, positive slope. ln3, a little bit steeper, but consistent. Every single place where y is 3, you have that same consistent slope. Here's what the field would look like for lny. So now let's go to the answer for the problem, which is x plus y. And so I think I'm going to toggle back now to the question, which said, shown above is a slope field for which of the following? You would bubble in C, although no multiple choice anymore, you lucky ducks. Not really lucky, don't envy you at all. But you would bubble in C once upon a time if you were taking a multiple choice. The answer is x plus y. And then I want to go back to the slope field to discuss y. So what I like to do when I'm trying to match or make sense of a slope field is just plug in a few points. So for example, let's go right here where x is -2 and y is 2. It makes sense to me that when x is -2 and y is 2, the slope would be 0. And look at how I have this horizontal tangent. Let's plug something else in. How about -3 and 3? When x is -3 and y is 3, I have this horizontal tangent right here. Let's go ahead and look at this random point at 2, 0. When x is 2 and y is 0, I have a slope of 2. In this field, this slope looks like it could be a slope of 2. If I'm still not convinced, I would maybe go to one more spot. How about right here at -2, 1? If I go to -2, 1, when x is -2 and y is 1, I get a slope of -1. This looks like it could be a slope of -1. I'm going to go ahead and pause for a moment. Okay, I'm back. I am now a couple pages down in this packet if you're following along with more with slope fields. I'm going to skip to another type of matching that you might encounter, especially with the Desmos activity. So here is a slope field that's drawn, and instead of having you match it to dy dx's, so reminder for the first problem, we matched the slope field with the derivative that could have generated that slope field. We determined that this derivative would have generated this field. Another type of matching that you're going to practice with your Desmos activity is not what derivative generated this field, but what antiderivative, what solution, which function is this field shouting from the mountaintops that it is? Like which solution could fit? Which solution could this be alluding to? If this field was drawn, what could the antiderivative, what could the solution be? So I normally just like put my pencil anywhere and then I just follow what the slope fields are telling me to do a little sketch. And the first place that I put my pencil really could be anywhere. If I make a sketch, it looks like it would be something not upside down parabolic, not right side up parabolic, but perhaps something more cubic. Specifically, this cubic. If I had put my pencil over here, I would start by going up, and then the slope fields tell me to go down a little bit, and then the slope fields tell me to go back up a little bit. So if I needed to match this slope field, not with the differential, but with the solution, with the antiderivative that it is talking about, I would pick part C. Another way to think about it is these are derivatives, right? And derivatives are tangents. So these are like little mini tangents to an invisible curve. Which curve are they little mini tangents to? And my choice would be part C. At this time, I'm going to go ahead and pause. And if you are playing along, if you have this packet, or if not, you can just look in the screen. Let's see if you could do this. So here is a slope field. And this time we are not matching it to differentials. We're not matching it to derivatives. We also are not matching it to the curves that are drawn. Rather, the solution's names, the curve's names. So do you think that this slope field is a match with A, B, C, D, or E? These are not derivatives. These are the solution curve yourself. So go ahead and hit pause. I will too, and then we'll see how you did. Okay, my friends, this looks rational to me. This looks rational to me. I could have parabolic branches here and here, or parabolic branches here and here. It is not a hyperbola. It is not an ellipse. Thank your Algebra 2 or pre-calc teacher for that. It is rational. Y equals 4 over x looks like a great contender. It is not parabolic, and it is not a circle. The answer for this is C. All right. So what you're going to do with Desmos is, and I'll put the assignment in Canvas, is you'll have slope fields, and sometimes you'll be matching them to derivatives. So y primes are derivatives. And you're going to look for little clues that could help you. For example, if the derivative is cosine, I know that the antiderivative is sine. So I would be tempted to match these two together. What's another one we could do real quick? This guy right here, 3x squared minus x. If that's the derivative, I know that the antiderivative is cubic. So I would be tempted to match it down here to this one. For things that I can't integrate or I don't really know the antiderivative of without doing separation of variables or something fancy, I would recommend when you're doing Desmos, just picking random points. So for example, I would match 3 minus y to this kiddo right here, because if I picked random points, when y is 3, look at these horizontal tangents. Look at these zero slopes. If I pick other points, like y is 2, for example, these slopes look like they could be 1. And so if I don't just know it based on clues about the antiderivative or things that I know from my past, then I'm literally plugging in points to try to figure it out. For something like xy, you're going to have to think about an x and a y. So you're going to go ahead and think when x is 0 and y is 0, I want the slope to be 0. When x is 1 and y is 1, I want the slope to be 1, and so on and so forth. I'm going to go ahead and pause because if this is too long, I'm not going to be able to upload it to YouTube. So hopefully this helps. If it doesn't, I'll make a clarifying video. So now that you've watched this, you are going to do the Desmos matching activities that I've put in Canvas. Thank you guys so much. Hope this made sense, and I'll see you next time.